Okay, yes, thanks for coming. Wow, Mumbai is a busy place. It took like an hour and a half to drive here from somewhere else in Mumbai. I thought New Delhi was big, but no. This is the third stop on the Jam tour. And the tour itself is becoming, I would say, does this not work? Hello, is that any better?
Test, test, test. Test.
Yes, this is the third stop on the tour, and it is evolving a little bit. So hopefully what you get today will be a little bit more punchy than what Cambridge and New Delhi crowds got. I'm going to start. I mean, thanks to Obi, we got like a bit of an idea about the historical context in which I'm coming to you talking about Jam. But I want to dwell a little bit on Web3, and it turns out that a guy called Sean Tabrizi has done some nice slides to help explain Web3 and Polkadot and what it's all about. And I think this is very helpful to give a sort of context for where Jam is coming from. Blockchain. It's been around now for a while, and about 15 years. And it was started by Bitcoin, and it was started in this kind of fairly cypherpunk way with this paper that was published anonymously. And it's clear that there were some principles that were adhered to with the creation of Bitcoin. And these are largely borne out for long-term thinking, essentially a desire to decentralize, a desire to anonymize, and so forth. And we're seeing an increasing fork in the ecosystem between long-term thinking and what might be characterized as more like short-term results-oriented stuff, where there's a lot of focus on early use cases, often those that have very questionable utility, like speculative tokens and trading, gambling, and so forth. It's somewhat unfortunate, and what I would like you to understand is that not all of those things that call themselves Web3 or call themselves blockchain out there are equal by a long shot. And we can sort of measure, there are various metrics that we can use in order to work out, like, which projects are kind of reasonable Web3 projects and which are not so much. Blockchain and Web3 are not the same, and nor are they the same as cryptocurrency. These things are rather different, and Web3 certainly isn't DeFi specifically. DeFi is just a vertical in all of this. It's a particular use case. Cryptocurrency, to some sense, is also a use case, but we might sort of consider it being a bit more general, some sort of resource that is in principle scarce. Blockchain is a technology that can help us implement these things, and Web3 is really a different way of thinking about the world and particular interactions and digital interactions in the world. And it's that I really want to talk about now. In some sense, Web3 is the embodiment or the solution to this concept of less trust and more truth. Now, it's a bit of an odd thing to say less trust. Like truth, yeah, we probably want to know the truth. But trust, that's a good thing as well, right? Why are we having less of it? And it's not per se that trustworthiness is something we want less of. We want, in general, more trustworthiness. But we're not talking about trustworthiness. We're talking about trust itself. And in particular, the requirement to trust when we don't necessarily want to. Trust in institutions, organizations, even individuals, particularly ones that we don't know and we have no reason to trust, is problematic. It tends to create power centers, and trust itself is not, well, by its very nature, is not something that you are able to objectively verify. The point of trusting is to sort of get something done or hope you've gotten something done without the need to sort of do it yourself or know that it's been done right. It's sort of, you trust someone else to do it for you. You have faith that it will be done for you. And this essentially offloads your sovereignty or a portion of your sovereignty to somebody else or some other group of people. And the purpose of trust is essentially that you do this on faith, right? If you had an objective reason to believe that whatever it was that you expect to happen actually would expect to happen, you wouldn't need to trust, yeah? It would be a rational decision. It's only trust when it's a sort of irrational decision. And this forcing of people to do irrational things is problematic, and it leads to problems, big social problems. And largely because those that are trusted actually have relatively little reason to do what they are trusted to do. Yeah.
Hello. Please. Hello.
All right. So there are a few different examples of where this requirement of trusting central entities have shown to be problematic for those individuals forced into this necessary relationship. And in the case of the first one, it was really an awful lot of individuals globally that this breakdown of trust affected. Centralized authorities should not be trusted. It's as simple as that. So how do we avert this approach? And it's an approach for solving various things. How do we avoid having to trust centralized authorities? Well, Web3 proposes to solve it by essentially introducing more truth, essentially giving individuals a greater amount of information that would then allow the individuals to not have to place trust in a central authority, but rather they'd be able to manage their affairs and achieve what they need to do themselves. Now, of course, we don't mean literally an individual getting out pen and paper and working out with information exactly how they will, run a bank or something. No, of course, the individuals have software. But the point of Web3 is that software, in principle, is analyzable by the individual. If you want, you can learn computer programming, look at the software, and work out exactly how it works. And ideally, if it's an open protocol, you can inspect the protocol in some much easier to inspect way and than necessarily looking at code, and convince yourself that given the information, something has happened or something is the case. Now, you can only do this if you have more truth, which is to say if you understand better how the protocols work and what everyone else is saying. For this, we need the internet, right? The internet is the only way of distributing truth fast, efficiently, and agilely enough. But we have the internet now, which is great, and it's really this that has propelled Web3 forward, right? And this Web3 means of averting the need for trusted authorities. Now, you can try and sort of dance around precisely what Web3 is, and a few people have offered up a few words, like 5 words or 5 terms, that try to sort of nail it down into a particular thing. I'm one of them. There's also Andreas Antonopoulos and Sean Tabrizi has also offered a sort of, we each have our sort of five dimensions, if you like, but they are, they broadly are getting at the same thing. I'm going to go into my 5, which are on the right there, a little later, but this is what we're talking about. And simply because something calls itself Web3 or has some technology in it that says it's a blockchain does not make it Web3. All right? This is crucial to understand. It is not a meaningless jargon term that you can just label your product with and then expect to sell and make lots of money. It has meaning behind it, right? And this is, broadly speaking, the meaning. And we can judge whether something is Web3 or not based on the degree to which it adheres to these principles. So Web3 is a different way of thinking about digital interactions between people and to some extent between people and organizations. It's just a different approach. So if you like, you know, I studied computer science way back when, about 25 years ago. And I went to a decent university to study, and they never taught anything about peer-to-peer. This was not a thing. 25 years ago, the way that you architected systems was always client-server. There was always somewhere that the data lived, and if it needed to be sort of distributed, then the ends of the graph would simply ask the server. Now maybe the servers there would be ways of distributing the servers, possibly, but the users would not be the distributed servers. They would necessarily be entities, bits of software that had to trust this server network or this server single machine. That was just the assumption, right? The assumption was that, well, of course the server is trustworthy. Why wouldn't the user trust the server? Yeah, we were modeling, in essence, this current or the traditional social structure where we have authorities, we have models of trust. People trust other groups of people. People trust each other. And we were just taking this model and naturally kind of fitting it onto computer architecture, systems architecture. Yeah, but it's a broken model. And it leads, as we have seen now, to massive amounts of global centralization, and particularly centralization of data flow. And overall, if you do this, you end up with a truly broken world. So what's blockchain? Blockchain is a decentralized computer. Okay? Now, a decentralized computer is a bit of a weird entity, right? It's a weird thing. So if it sounds odd, don't worry, it is odd. Computers are not decentralized. They are physical things. I am a person. I'm not decentralized. I'm a physical thing. It would be very hard for me to be decentralized. I mean, it would be a very odd, odd thing indeed. Now, a computer, because computers are fundamentally mathematically modelable, what we can do is create a model of a computer and have it not exist in any one particular place, but rather either be replicated or be sufficiently reproducible across multiple partial replications of it, that we're able to rebuild the final model of the computer and understand what state that computer is in. Right? At the end of the day, if you want to know what state a computer is in, broadly speaking, you just need to know what its CPU is doing and what its memory's got in it. Right? Maybe if it's got some storage, what that's got in it too. Yeah? And you can for all intents and purposes, you can recreate that very machine. Even if it's on technically different hardware, it will still have the same output, and that's what we care about. So blockchain actually is this, right? Now, when we talk about blockchain, most practitioners of blockchain will talk about hashes and hash-linked lists and cryptographic commitments and transactions and all this stuff. I mean, that's fine, And those are important details if you're going to implement a blockchain. But if you just want to know what a blockchain does, well, what it does is it's a computer. Yeah, it's just a computer that doesn't exist in any one particular place. It exists on the internet. It's an internet computer. Yeah? If there were only one node, then it would just be a VM, right? It would just literally be a virtual machine. You're just running a virtual machine. But because there are many nodes, and because we presume there isn't just one single authority that decides what this computer is doing at any given time, then it becomes a decentralized computer. Now, of course, the degree to which it's decentralized depends on factors such as how many economic agents would it take to collude to break the computer or make it do something it's not meant to do. Yeah? And if it's only a couple, then it's not very decentralized. So, I'm not going to go into that. So I want to, Obi mentioned that, that this broad manner of thinking, of making computers work for people rather than work against people, this is something that has been running for a long time. Basically, as long as computers have been, as long as it's possible for people to buy computers. And really, this whole Web3 blockchain chapter is just the most recent chapter of this long journey. But it is worth focusing on it because it's only when we do that we understand the specific technical advances that we're making and why. So Bitcoin essentially started this concept of a blockchain off, this decentralized computer off, and it was a decentralized but domain-specific computer, more like a calculator. It could do particular few jobs. When we came to develop Ethereum about 10 years ago, we wanted to make it more general. Now, the word that we were using at the time, although I kind of shuddered a little bit when we did, was Turing complete, right? Now, I never particularly liked this term because it's not really Turing complete. It has this concept of gas, which is a number of computational steps. And by limiting how many computational steps any given operation is allowed to do, you can make sure that any particular person on the network, any node on the network is able to actually evaluate the machine's state, right? And we can come to a consensus over the state of this decentralized computer. So actually we limited the number of computational steps, and therefore we limited its effectively the number of programs that it could run. Yeah? So it's not really Turing complete in that sense. However, its scripting language, the language that it used to actually encode its computer programs, ignoring the fact that the programs had to be limited in the number of steps that they could take, was Turing complete, and this was a change from Bitcoin. So it did make sense to make that point. After Ethereum, which was really a synchronous computer, right? It sort of had one execution core, and this instruction set was, we can call EVM, the Ethereum virtual machine. It's kind of execution architecture, execution instruction set. It therefore didn't really have great performance. Yeah? And we see this today with the Ethereum network, finding it hard to process everyone's transactions who wants to. The price of gas, the price of this computational resource has gone up. It spikes quite often. And we see an increasing move to other chains in order to chase capacity for decentralized compute. One of the other chains, and the chain that I was working on for many years, is Polkadot, which took the concept of a general purpose decentralized computer and essentially said, well, what if we could make lots of computers but secure them under the same roof, essentially allowing multiple different sovereign economies to share the cost of securing themselves and also provide message passing between the economies. Now, we call it sometimes a multi-core computer or cloud server. For the current version of Polkadot, it's probably better to think about it as more like a sort of a LAN of single core CPUs, right? Yeah, because they can send messages to each other, but they don't share memory. They don't share any storage. Yeah. And I mean, Polkadot essentially is a multi-chain, right? It's multiple blockchains, co-secured. But each blockchain is independent. I'm going to come back to this, but it is an important point. It's something that Jam deviates from. So what's the main difference between Web 2 and Web 3? I've sort of told you, well, Web 3 is less trust, more truth. I've told you why we want to do it. I've told you how, more or less, we're doing it. But what's the crucial difference that we want to achieve? Well, it's resilience. We might talk about decentralization. And for sure, decentralization is an important part of gaining resilience. We might talk about cryptography, also an important part of gaining resilience. We might talk about game theory and economics. But the thing that we're actually attempting to achieve is resilience. And it's resilience not just like, oh, it breaks down less, right? We're talking about resilience as in the ability for it to withstand anything this world can throw at it on its own without a protector. Yeah, normally, software systems have a protector. They have the organization or the person that is running them. If I run software on my laptop, I am its protector. I am the person that is preventing the laptop from being shut down, from preventing the software from being deleted, preventing the process from being killed, right? I am the protector of that software. Well, when we come to Web 3, we want software that can exist without a protector. And in principle, if the software can provide its own economic incentives, then that software should be able to run without, well, anyone at all, particularly caring about it. There are lots of things to be resilient against. Other pieces of software, other teams of individuals, all the way up to sovereign nations. And Web 3 has to be resilient. Truly Web 3 software and systems have to be resilient against all of these things. And that's hard. One of the very interesting things that Web 3 systems must be resilient against is their own deployer, right? The individual or the organization that created them. Now, normally, this would be mad. It's like, why would you want something to be resilient against the individual or the organization that created it? Surely that's the one thing that you can be certain it doesn't need to be resilient against. They wouldn't have created it otherwise. Well, it's true, but the problem is that systems and their creators are not the same entity. They are different economic entities. They have their alignment and their needs can diverge. And oftentimes do diverge. And this can become very problematic. So it's important to treat essentially everything outside of the Web3 system, outside of the software or the protocol, the network, whatever it is, everything outside of it as a potential problem, a potential malicious, malevolent force, and to make sure that the system is protected against it. Nothing is trustworthy in the eyes of Web3. Okay, so what does it mean to build a Web3 cloud? Well, we've talked about decentralized computers. A Web3 cloud would essentially be a bunch of decentralized computers where you can sort of rent out processing time, right? That's what a Web2 cloud is. Still centralized, obviously, whether it's Amazon or Microsoft or Google or whoever's running those computers. You are paying that particular organization, and you are trusting that organization with your data, with your potential economy, your business, right? And of course, you can't just trust them. It would be an interesting world. It would be a nice world if you could just trust them. But you actually also have to trust any other entities above or within them. So you have to trust employees, you have to trust their processes, and you have to trust any sovereign nations that they might be under the rule of law of. And this, as we have seen in the past, is not always something that you can trust or something that you could possibly know when is trustworthy. So a Web3 cloud would be sort of a trustless version of that, a version where you don't have to trust any particular entity and all of its processes and employees and da-da-da-da-da. For a cloud, a Web3 cloud, we're going to need to build a Web3 supercomputer, and then we're going to need to build lots of them. That's the way that we build a Web3 cloud, right? Powerful computer, but lots of powerful computers kind of able to work together. What is Web3's main resource? Probably, I mean, this is a little bit arguable because it's not exactly clear what block space is. It's certainly processing resources, but you could also maybe argue it's the availability of data, the ability to store and retrieve data at some later time. And there's maybe messaging as well, the ability to pass messages between disparate entities. There's a few different things resources that we might think Web3 is. But certainly one of them is block space, and one tighter meaning of block space is essentially this computational resource, this processing power on a decentralized computer. We can measure block space in a few different ways. Block space is not all the same type of stuff, although of course those who are peddling low quality block space will do their best to argue that it is, but it's not. And I can show you a few different ways of measuring block space, of understanding the different qualities. For what it's worth, Polkadot is designed to create the highest quality block space, and Jam is designed to increase that again. But let's look at Polkadot first, and we can understand how Jam improves on it. So one of the ways that in the Web3 industry, we measure how high performance or how scalable a particular system is for block space is by measuring the number of transactions they can do per second. Transactions are basically like balance transfers. It's not a great way of measuring the performance of a blockchain, right, of Web3, of block space, because what one system considers a transaction may be different from what another considers a transaction. There are all sorts of different ways of doing transactions. But broadly speaking, for transactions per second, I mean, this is on a live system. It's actually not on the Polkadot network. It's on the Kusama network, but it uses the Polkadot protocol. And it was getting well over 100,000 transactions per second. And these are like proper user transactions, not like lightweight system transactions, right? They are actually balance transfers going from between two independent accounts. And as you can see, that's substantially larger than anything else. Okay, so what's that? Like bandwidth, data bandwidth. How much data can we get in and out of the system, in and out of this decentralized computer, right? You can think of this as like maybe the memory or the storage bandwidth, right? In Polkadot's case, it's 42 megabytes per second, right? Again, substantially greater than even domain-specific data availability solutions, and orders of magnitude greater than some of the older blockchains. One very important way of measuring block space is how resilient it is, and in particular how decentralized it is. How many economic entities would need to be compromised, hacked, paid off, or malicious in order to compromise the actual network itself, break the computer. And in Polkadot's case, it's very high compared to basically any other significant blockchain, right? 5x over the next. Ethereum's not on this graph, it's even lower, right? It's 2 or 3. And then we can talk about like energy efficiency. Like overall, how much does it cost to actually run this decentralized computer? If it's running over lots of nodes, maybe it costs a lot. In fact, in Polkadot's case, it's far, far lower than anything, any of the other vaguely fast decentralized computers. And this is largely because Polkadot actually distributes its workload over its node network. It doesn't try to make every node all do the same work, right? It's a classic approach, right? Divide and conquer. I'm sure you all know about it. But Polkadot actually does it. Yeah? Most of the other networks just throw a lot more money and energy at the problem. So yeah, Polkadot is able to parallelize its computation, not parallelized on the same machine. That doesn't really get you so far. But parallelize computation over its node network, distribute it across multiple computers. As I mentioned before, it provides shared security so that we can have all of our computation existing under the same security umbrella, essentially pooling different economies in order to share the costs of security. Polkadot pioneered the concept of interoperable blockchains, the ability for different systems to be able to send standardized messages between each other and do all sorts of rich interactions via these standardized messaging systems. The messaging itself, XCM, cross-consensus message format, is in its 5th revision, 6th revision now. And the need for a message format, you can understand this better if you understand that they don't share memory, they don't share storage. These different blockchains are very much their own independent state machines. And therefore, there is a need for them to send messages between each other in order for them to have some sort of interoperation or interaction. And of course, Polkadot provides data availability for its systems, for its blockchains. Now, actually, this data availability is specifically for the security system that it needs. But JAM, one of the sort of important things that JAM does is it increases the value of this data availability system and the capacity. And we'll see that in a second. So that's Polkadot, leader of the technological pack at present. JAM is the next iteration, in some sense, of the Polkadot protocol. And it's really a reimagining of Polkadot's core technology. Now, JAM is a very different approach to what we've had before in Polkadot. Polkadot was a very software-oriented approach. Parity Technologies, the company I founded, built the software that ran Polkadot nodes. At some point later, a sort of standards document was produced that did a technical specification of the Polkadot protocol that was mostly complete, allowing, in principle, other teams to re-implement the protocol, make alternative implementations. There are actually 2 other teams that the Web3 Foundation sponsored to create alternative implementations of the Polkadot protocol. In reality, those teams were pretty heavily dependent on that first implementation. The code that they scoured the code, treating it essentially as a reference implementation. Any bugs in that code would be also in the other 2 implementations, probably. Now, this is problematic, and it kind of reduces the value of having multiple implementations. The reason that you have multiple implementations of a protocol or a software system is, of course, diverse implementations, avoid the possibility of a single mistake taking down the whole system. Yeah? Used in various mission critical scenarios or mission critical or life and death software situations in order to prevent the possibility of a software error from breaking the whole thing. Planes, for example, will typically have 3 different control systems, each engineered independently to the same overall protocol standard, and then actually in real time, actually on the plane, run all 3 on different hardware, both hardware and software, and just take the 2 that seem to agree. I mean, most of the time, all 3 should agree with each other. But if one of them happens not to, take the 2 that do agree. In essence, a small consensus system, right? And all we're doing with blockchain, in some sense, and particularly with Jam, is taking this to the max. So Jam is protocol-oriented. What does it mean? Well, basically it means the protocol is specified in a technical specification paper, the grey paper, before it's implemented, or at least before the implementation is public. Now, no one's just going to wake up one day and say, I'm just going to implement this rather complex protocol. I mean, probably. So there is some incentivization for them to do this. And one of the important bits one of the sort of really tangible bits of incentivization is the Jam Prize. It's a large prize fund of crypto for anyone who actually implements the grey paper according to their conformance and performance tests. Now this sort of covers getting implementations out there, but oftentimes when you have multiple implementations and you're looking for emergent effects, right? This is what this is all about. We are not coding the effects, the effects that we want to see directly. We're not designing for them sort of directly. We're designing systems so that the effects that we want emerge as the behavior of multiple nodes running this software. Yeah? And this is a kind of funny thing. What it means is that if you just run it once, you may have a qualitatively different outcome than if you run 1,023 instances, even though it's a peer-to-peer system. Now, in order to as systems get more complex, those emergent effects become ever more unpredictable. Small changes that apparently should make no real difference from the perspective of the implementation can have huge knock-on effects when we look at the emergent behavior from many different implementations taken together. And so one of the things that we really need, much more so as protocols become more distribute work around, become more sophisticated. One of the things that we really need is an experimentation rig where we can actually analyze the emergent effects in real time, lay down 1,000 nodes and see what happens when you break the networking, or you slow the networking for these nodes down, or you change this parameter on half of them, or you use that implementation for a third of them. Yeah? Or you run it at full, you run massive amounts of work through half of the cores and no work through the other half. Or you use storage in this part, but only compute in that part. There are all sorts of scenarios that we need to understand, firstly, if they work properly, like maybe there are bugs, but secondly, if they work optimally. Is the performance of the empirically analyzable performance in line with our models? And if not, why not? And this investigation is hard when you're doing it on a production network, even on a sort of decentralized test net where you have many different operators, each running validator nodes. Really what you need is for them all to be able to be run under controlled conditions. You need repeatability. It's classic software engineering. And in order to do that on a massive global decentralized network, well, it's hard. So what we do is we create a model. We create a sort of a proper full-scale model of the eventual Jam network, but we put it in one place. All right? This is called a jam toaster. And basically, it's a small supercomputer that can run at full scale the whole jam network. Attached to this, of course, is lots of logging and analytical software and so forth in order to visualizations, in order for us to see what's going on in any given situation and dig out any potential sources of suboptimal performance. Okay, so the grey paper follows on from the yellow paper. As Mila mentioned, I published it 10 years, almost to the day. I think I was a day out, 2 days out, after the yellow paper. So the yellow paper was the formal specification of the first Ethereum protocol, the first production Ethereum protocol. And the grey paper, once it gets to version 1.0, will be the formal specification of the genesis of the jam protocol. The formalisms used are pretty similar. The general structures of the papers are pretty similar. But of course, the contents for the grey paper are quite a bit more sophisticated. I tried to keep the level of opinionation and the overall complexities down as much as possible. But it is not the simplest protocol, and it's certainly not as simple as the Ethereum protocol. In terms of the number of pages, I think it's about 64-ish pages. Now, Ethereum, I think the current yellow paper is maybe about 50. So it's like, in terms of bulk, it's not actually that much more. But in terms of density, and particularly density, sort of logic density, rather than straight like crypto maths description density, it's pretty, it's quite a bit higher. So the Jam prize, as I say, it is a prize fund. Meant to incentivize individuals or teams that are implementing the grey paper, Jam. So the prize is it's quite a large pot. It's 10 million DOT and a bunch of KSM as well. And it's centers around 5 milestones. So each one you're going to do in order. The first one essentially is just able to recognize valid blocks or a valid blockchain. The second one is able to extend the blockchain in a sensible fashion. And then the third, fourth are both optimizations, so basically just getting the right performance of block authoring and importing. And then the final milestone is really just passing an independent security audit. Yeah. Each milestone gets each milestone gets 100,000 DOT. So in total, there's like 500,000 DOT per implementation. A fairly substantial amount. And there are a bunch of other bits of support beyond just the straight prize. There is an on-chain fellowship for Polkadot, and essentially you get a membership in the fellowship, and I think for each milestone you kind of get one extra rank or person into the fellowship. Now fellowship comes with like voting rights. You actually get some control over the protocol's future. It comes with salaries, like stable coin-based salaries. It comes with, obviously that fifth milestone requires a professional audit that's paid for. Comes with invitations to international seminars, talking about the protocol, meeting other teams. It comes with hardware access, significant, like powerful hardware to test out implementations, and of course Jam Toaster access for running massive scaled trials on proper hardware. To avoid everyone implementing it in the same 2 languages, there are language groups. And the prize, the total prize fund, the 10 million DOT, is split, so it's 2.5 million DOT for each of the 4 language groups. And once the language group has paid out all of its 2.5 million DOT, then it's like there is no more left in that language group. So essentially there is an incentive here to pick a group that not many other people or fewer people are writing an implementation in. I think at the moment there's quite a few implementations written in language groups A and B. And if you're interested to find out who is writing or who is saying that they are writing an implementation in what language. You can go to the greypaper.com website and have a look. They're all listed there, all the publicly known ones. Of course, there's no need to actually tell anyone. You can always write it in private and then just submit it once it's finished. It is a prize after all. So the Jam Toaster, as I said, is like a small supercomputer. It doesn't really compare to modern day supercomputers, especially with them mostly being GPU computers these days. But you know, it's also substantially more powerful than basically what you're going to find outside of a data center. So it's got 16,500 5 gigahertz Threadripper cores, and these are like basically top of the line AMD cores. An awful lot of L2 cache. Basically, all of them have a 1 meg L2 cache. A lot of RAM and very effective networking between each of the actual machines. On this computer, there will be all 1,023 jam nodes that would make up a full complement jam network, and each node should have access to 16 cores and the according amount of memory and storage. Good. All right. So, what is JAM? Well, it stands for the Join Accumulate Machine. But before I go specifically into how JAM works, I want to talk a little bit more about the principles of Web3 and how they relate to JAM. What makes JAM special? Why is it considered an upgrade? Why is it a Web3 protocol? Well, Web3 is based around, let's start with Bitcoin. Let's take a historical view of Web3. Now, Bitcoin had a certain, it was a very resilient protocol, right? The fact that it still exists and does the same thing that it's been doing for 15 years indicates that resilience. Yeah, it hasn't been shut down. It hasn't done anything that is hasn't gotten corrupt or done anything that would break its original set of expectations. Presumably, Satoshi Nakamoto, wherever they are, is pretty happy with how it's gone. But it wasn't a general protocol. It couldn't generally do tasks that we would use computers for. It was a very domain-specific protocol, right? It solved the ability to send balances between accounts. And there's a little bit of scripting in there too. It also wasn't an especially high-performance protocol. Now, these three things are really what we understood, like how we measured blockchains up until not all that long ago. And when we did Ethereum, the thing that we were solving for, the thing that we understood Bitcoin to be not so great at, was that generality point. We wanted to keep the resilience and make performance not too much worse or ideally a bit better, but really it was the generality that was the big step forward. Now Polkadot comes along and says, right, now it's time to do the performance. We've got the generality, we've got the resilience, let's make a protocol that is both resilient and general and performant. And how did we do that? Well, we did it by creating a multi-chain. We did it by essentially taking the existing technology and making it scale out across 50, 100 different chains, thereby achieving this substantial increase in performance. There were a few other tricks that we did. So actually the increase was more like 500 or 1,000x. Yeah? The thing that Polkadot doesn't share with Bitcoin and Ethereum, however, is coherency. Taken as a whole and taken as this like parachains host, there is no coherency in that different entities inside of Polkadot may be able to interoperate to different degrees. I'll give you a very simple example. If you have two smart contracts under the same parachain, and if you're wondering what a parachain is, it's a blockchain that's secured by Polkadot. Two smart contracts under the same parachain can interact with each other, generally speaking, much easier, much faster, much cheaper than two smart contracts that are sat in different parachains. This is not the case in Ethereum. Disregarding Ethereum L2 and all this stuff, in the original Ethereum network and in Bitcoin, any two accounts, any two smart contracts can interact with each other just as easily as any other two. They're all in the same state space. Yeah? And this is a crucial thing to understand, because it's this coherency quality that is currently being traded off, not just in Polkadot. Polkadot was merely a trailblazer, but all around in this industry, blockchains attempting to scale themselves out. So really what we're talking about here is the desire to get resilience, generality, and performance, just like Polkadot got, but also keep coherency, or at least keep most of it. And then there's a question how we do that, and it's an interesting question. It's interesting because it's got a little bit of a philosophical lilt to it. Coherency, which can also to some extent be considered the same thing as synchrony, is a fundamental antagonism with scale. As systems scale, they fundamentally get less coherent or slower if they remain synchronous. Why? Well, essentially, as systems grow and there is more information, that information has to travel further distances on average, and the overall variance of all distance traveled grows as more entities are in the system, right? So if you picture the system, as the system grows, you plot the different sort of entities. Imagine each smart contract is at a point in this space. Those points, if you take any 2 points, those points are A, more likely to be further apart as the system grows, and B, the distribution of distances is more likely to be greater. Like the variance of that distribution is more likely to be greater. So we see both the mean and the variance increasing of overall distances between any two parts of state. Well, what does this mean? Well, we know that information takes time to travel at a very, very tangible basis. That's the speed of light, right? But computers, broadly speaking, don't work at the speed of light. They work more at the speed of electrons. But even still, the point is that it's not possible to grow a system, generally speaking, without compromising either the speed, the overall speed at which it goes, or the coherency, the fact that some things will interact sort of out of order or faster than other things. That there isn't really a way of sort of nailing down what state the system is in. It will be an interminable state because some things may have finished before other things. Yeah? And actually, if you go to hardware, looking at like CPU design, you'll find this exact same problem. You'll find that the pathways on a CPU die will be specifically designed so that things may take slower to arrive, but they will all arrive at the same time, more or less. Yeah? Some paths will be longer than they need to be, and they'll route them around to keep the coherency, even at a cost of speed, at least speed of some of the interactions. So we have the face of the same thing in blockchain. As we want to scale them out, we have either a synchronization problem, like a coherency problem, or a speed problem. Either everything has to go a lot slower, or we have to work out how to manage this reduction in coherency. Now, the way that we've managed it so far across the industry for those participants that are actually scaling out is by basically just splitting it up. Yeah, we just carve it up, partition it, right, the state space, into just independent bits. And then the only way that these bits can talk to each other is by sending messages, which are asynchronous and slow and generally very small. Yeah, that's the basic assumption. There's a few, we can do maybe passive reads from certain other states, but it's all very haphazard. There is no real way of attempting to split or manage coherency in an agile fashion. So if we look at Polkadot, thus far, it does exactly this, right? It's achieved a lot. It's achieved a lot of impressive things. It's decentralized, it's distributed, it's resilient, it's fast, it's performant, it can scale out. But it does this through a persistent state partition. It has partitioned its state up between the different parachains. Yeah? And when something is on one parachain, it stays there. It doesn't move. It stays on that parachain. And if it wants to interact with something on a different parachain, it has to send a message. It can't immediately compose itself. It can't do anything atomically. It's very hard to get atomic interactions if things are in different parts of state space. Now, Polkadot also had a slightly other issue, which was high barriers to entry, right? Deploying something in Polkadot, deploying a blockchain in Polkadot, parachain, it's not as trivial as deploying a smart contract. That's the reality. There are a few hoops that you have to jump through. Now, of course, you get a lot for those hoops. You get a lot more flexibility and so forth. You get a lot more power. But you still have to jump through them. And if the thing that you want to do happens not to need that flexibility, then it can seem quite daunting. If we compare it to Ethereum, and specifically Ethereum as it stands today, we see it's costly, it's slow. I mean, this isn't particularly surprising. It's 10 years old now. But it's patchy. So the Ethereum approach is similar to the Polkadot approach, right? It's just that we're 5 years behind. Now, when I say patchy, it's actually patchier than even the Polkadot approach. Polkadot had a very standard parachains model, right? A standard way of introducing and securing L2 blockchains, or parachains in Polkadot's terminology, into Polkadot. And this meant that it was relatively easy to agree on things like the messaging format, to agree on things like the latency for messages being passed around, to agree on things like oracleizing state data between parachains. This isn't the case with Ethereum L2s, which is why, in part, Ethereum is now talking a lot more about native rollups. Essentially, parachains. Don't tell them that, but that's basically what it is. Now, the problem is with another of the approaches, well, with this approach, is what we've found with Polkadot, which is that there is a persistent state partition. The different rollups each have their own state that is looked after by their individual network. And that state doesn't easily make its way onto other rollups. In essence, when you deploy to Polygon, you are specifically tied to the Polygon ecosystem. You are not going to be able to interact nearly as well with OP-Stack or with Arbitrum or with any of the other L2s, or indeed with the L1. Now, the other issue that Ethereum is inevitably coming across is as Ethereum relies more and more on the ZK mechanisms for rolling up data or projecting, sort of compacting correctness into smaller amounts of compute, the ZK elements provers, the proof generators, have a necessarily centralizing effect, essentially due to the winner-takes-all aspect of proof generation, right? There's not that much point being second, and therefore there's not that much point running a node that, or running a proof generation node that will consistently come not first. This leads to one proof generation node being worthwhile running. Now we've got a few other approaches as well. One of them is bridged chains. These are chains that have their own security mechanism, their own economy, their own validator set, their own security guarantees. Inevitably, these will be different to any other chain security guarantees. These chains would then be bridged, with the assumption being that if a message comes signed by some portion of the validators of one chain, it's fine. You can treat it as certainly coming from that chain. And of course, the issue is that if the bridge message has some effect, some causal effect on its destination, then that effect is secured only by those validators. If those validators happen to be compromised or malicious, then that effect is, in essence, toxic to the destination chain. Taken to its eventual conclusion, it means that a system that is built on lots and lots of these bilateral bridges will only be as secure as the weakest secured chain. Yeah? And it's because that cause and effect coming from the weakly secured chain will be, in essence, able to poison the rest of the system into doing something it's not really meant to do. Now, of course, there are some caveats here. It may not have that much of an ability to affect things, but nonetheless, networking in this way, sort of allowing cause and effect to take place from weak chains, is problematic. You wouldn't bridge in a test net and expect sensible things to happen, right? And essentially, we're talking about this kind of same thing. And moreover, it's still persistent state partitioning, right? The different networks each have their own state, and that's independent to all of the other networks. You still have to choose, if you're a team looking to deploy a smart contract somewhere, you have to make your choice of which chain to deploy it onto. Another approach is basically just to do what Solana does and throw money at the problem, right? Just make validator nodes really, really powerful and insist that they have to be really, really well connected. Now, the more that you raise the requirements for taking part in a decentralized network, the less decentralized it becomes. Yeah? And there's inevitably a trade-off. We don't necessarily want everyone to be able to take part in running a network on their old Nokia phones, right? But if we make it so that, well, you have to more or less be co-located if you're going to be a serious validator on the network, and you have to have 512 gigabytes of RAM, and you have to run with this particular CPU model, we end up having a potential centralization issue. We end up having potentially just an exclusive group, an elite group of participants that are capable of being validators, and everyone else just kind of has to trust that these guys do a good job. We also see that as we introduce more and more software optimizations to make a single node go as fast as possible, we introduce fragility into the system. This is particularly the case when we don't have a comprehensive and fundamental protocol specification, when it's not a protocol-oriented system, but instead a software-oriented system. And ultimately, these systems are unscalable. There's a reason that in Silicon Valley the mantra is scale out, don't scale up. Yeah? Ultimately, these systems will only process transactions as fast as one machine alone could process transactions. That's the end game for this. And actually, that would imply having just one node on the network, and therefore it wouldn't be Web3 at all, it would just be a regular Google server. As we increase the number of nodes on the network, we have to distribute, we have to publish the data between the nodes, they have to stay in synchronization, and this therefore means you're probably not going to be able to run as fast as one single node could run, because it has to take some sort of time to send the data out and synchronize with the other nodes. There has to be some handoff protocol, which inevitably is going to slow things down. So these systems, this is not a scalable approach. This is a short-term approach to try to eke out as much performance as is possible, knowing that we are not going to run too many validators on our network. So what does Jam do? Well, Jam, like Polkadot, scales out, not up. It keeps the requirements for its individual validator nodes to be relatively low, right? 16-core AMD processor, maybe 32 gigs of memory, this sort of thing. Couple terabytes on hard disk, NVMe, pretty standard server requirements. So how does Jam, the protocol, use these relatively modestly powered nodes to be able to present a supercomputer, and in particular, a supercomputer that doesn't suffer from this problematic of like incoherence or decoherence? Well, essentially what it does is it reduces the decoherence to be transient decoherence. So the system is sort of allowed to kind of make itself decoherent for a little bit, but every 6 seconds the system becomes recoherent. Yeah? In between these 6-second kind of milestones, the system sort of goes off and does its own stuff. Now the crucial thing is that when it reconvenes every 6 seconds, after that point, or at that point, everything is coherent. Yeah? There is only one state, and it's shared by the whole machine. It's like we have a single state that isn't partitioned at all every 6 seconds. So that partitioning is agile, and it only affects the machine during the 6 seconds, not at the 6-second milestones. Now this requires a different model of computation, and that's why we have this, there's the in-core on-chain terminology. There's also what I've called refine and accumulate. Refine and accumulate is like the interface. The in-core and the on-chain is more like protocol level, but basically refine is done in-core and accumulate is done on-chain. Refine in core is stateless apart from access to this big data lake, which is basically like a data lookup system, right? Accumulate on-chain is synchronous and it's stateful. Refine can pass data into accumulate. And that's about it. That's about what you need to know for this model. Now, if you wanted to share data between the different computational elements, well, that's easy, because everything gets synchronized, everything goes into this distributed data lake, this giant storage system, every 6 seconds. And therefore, you can read out of the storage system what you wrote in past blocks, in past 6-second periods. Now, the actual data lake, for what it matters, it's not so important, I don't think, but for what it's worth, it's a 4 kilobyte, data is stored in 4 kilobyte segments, and these segments can be fetched with a sort of cryptographic identifier that just identifies which block put the segment in, basically, right? It's like a 36-byte identifier or something, 32-byte identifier, I think, 34. And if you know this 34 bytes, which you can find out just by sort of putting it in. When you put it in, you get this identifier back. Then you can look it up again at a later stage. Yeah? It's sort of like an address in storage. Now for those, if you're familiar with more Ethereum terms, I can rephrase this in Ethereum terminology. It's like my Esperanto of blockchain. So if you like, you can say, well, Jam hosts 341 Turing-complete L2 native rollups. And it also has a Turing-complete smart contract chain, L1 chain, that these native rollups sort of fold into. The rollups, although they are stateless, they have common access to a massive distributed decentralized availability system, 1.6 petabyte distributed availability store. synchronized every 6 seconds. So every 6 seconds, it becomes the same store, regardless of where you are in the whole of Jam. You're still looking at the same store. You can still read and write or read the same data that anything in Jam has written at least 6 seconds ago. If you happen to be on the same computational element as the previous 6 seconds, they all have indices, right? If you happen to be on the same index element, kind of like the same CPU core, if a process is scheduled on the same CPU core, then this reduces to 0. What this means is, very similar to CPU design and operating system scheduling, if you happen to be scheduled in the same place, when you write something out to storage, you can read back from it without any latency. Yeah? If that's the case, if you happen to be sort of scheduled on a different core, a different computational element, then the thing that you wrote out, you have to sort of wait 6 seconds. It might be 6 seconds. You might get it earlier, right? It might be 0 seconds. But either way, it will only add latency. It won't alter the correctness, right? The correctness will do the same thing regardless. It's just it will do it a bit slower if you're on a different core. Possibly. We have what I call cynical roll-ups. This is a sort of tongue-in-cheek term, a little to sort of as a bit of a kick in the teeth to optimistic roll-ups, which I call pessimistic roll-ups. They're not optimistic at all. They're pessimistic. If you're not familiar with pessimistic roll-ups on Ethereum, they're actually where most of the L2 computation is done. And essentially what they do is they say, we think this is the right result, but we don't know for sure. So if anyone can prove it's the wrong result, then we'll wind it back. And until we've given enough time for someone to prove that it might be the wrong result, then we won't treat it as final. Yeah? And it's like, all right, well, how long are you going to wait? Oh, well, we'll wait 4 days. 4 days. All right, so if I do a transfer, I wait 4 days on the off chance that someone somewhere detects it's the wrong thing and tells the L1 about it. All right, this seems a bit overly pessimistic. Why would it take 4 days but not 4 days and 10 minutes? Oh, well, 4 days should be safe. We're being conservative. Okay, I call it pessimistic. I call it a pretty dumb protocol, which is why we came up with our cynical rollups protocol, which is a little bit like optimistic or pessimistic rollups in that it is proposed that some particular computation has some particular result, and that is posted, that proposal, plus a certain deposit for saying, for betting on it being the right thing, essentially, is posted to the L1 chain, ready for others to come along and potentially provide a fraud proof. The key difference is that in Polkadot and Jam, we make sure that there are validators out there, entities, economically incentivized entities, that make money by posting fraud proofs fast. Yeah? We also make sure that enough of them will self-select for checking these fraud proofs, that it won't take very long before we can get a really strong level of confidence that at least one honest actor will have checked and made sure that this thing is legit. Yeah? And once we get to the point of being essentially certain that at least one honest actor has checked this thing and has decided that it's fine, then we say it's final. And it turns out, if you do it well, like we've demonstrated with the ELVS research paper, then it takes maybe about 6 seconds instead of 4 days. We also have anonymous block authoring. Why does block authoring need to be anonymous? Well, it's anonymous up until the point that the block is published, at which point it doesn't really matter whether it's anonymous or not. Why does it need to be anonymous up until the point the block is published? Well, it's very simple. Because certain attacks rely on the ability to prevent blocks being authored for a little while, right? These might be economic attacks. These might be attacks that simply prevent, say, some money being taken out of an account, or some particular liquidation from happening. It doesn't really matter. But the ability to stall block production is and can be a very important part of an attack, and therefore it's important that we make sure that a block author has as much chance as possible of getting their block published. They may not have very much of a chance compared, against a determined attacker if it's already known precisely what their IP address is and precisely when they're going to publish this block. Yeah? It's very simple to mount a DOS attack. Jam doesn't rely on look, it builds in its own look. And this is Safrel. It's actually a it's a refinement of another protocol published by the Web3 Foundation as well, called Sassafras. But basically it uses zero-knowledge proofs as a way of avoiding giving away when it's legitimate for you to produce a block. It also has near-instant finality, and that's delivered by another protocol called Grandpa that uses some quite clever game theory in order to deliver very fast finality when there is good network conditions and degrade gracefully into providing still quite fast finality even when there are bad network conditions. All right, so Jam pipeline. What does Jam actually do? How does it sort of work? Well, when work is presented to Jam, it goes through a few different stages. And it's important to know a little bit about these stages. The first stage that work goes through is what's called authorization. Authorization makes sure that it's reasonable for Jam to do this work. Yeah? Jam is designed to be out there in the wild. It would be mad if Jam couldn't determine what work it should be doing before it started doing the work. How do other systems do this? Well, generally, you can look at two different models. One of them is the Ethereum Bitcoin model, which is where you pay up front for every little bit of work that you want to do. The way that we pay it is through gas, right? So we basically say, I want this amount of gas, and I'm willing to offer this amount of funds, this amount of assets, this amount of tokens for that gas. And then we have some validators, the block author, that will select some of this work to do based on how much they're going to get paid from the authors of the transactions. That's one way of doing it. Basically a very immediate sort of agile market for computational workload. That's fine when we're talking about little transactions, but when we're talking about the sorts of things that Jam is doing, which is, many orders of magnitude of greater power, it doesn't make so much sense. Polkadot's model maybe makes a little bit more sense. So Polkadot's model is where we have the ability to purchase large amounts of block space, of processing power, ahead of time in auctions and then trade it around before it's being used. In essence, we buy a little chunk, or potentially a very large chunk, of the Jam computer, but a period of time for using, almost like on, actually very similar to AWS, to like Web2, cloud, right? You will rent a cloud server. You'll rent a cloud machine, yeah? And you get access to that cloud machine for whatever, a day, an hour, a month, yeah? And you just buy that at a time. It's some amount of time on a computational resource. Well, it's exactly the same with Jam, with Polkadot. You buy, in essence, time on the Polkadot computer or time on the Jam computer. Authorization allows Jam to understand whether the work is worth doing. Work comes as packages of work packages, which essentially is just a bunch of information describing what Jam should be doing, right? What work Jam should be doing, what data Jam should be taking, what software Jam should be running, that's basically it. And it doesn't really come down to much else other than passing data into algorithms. There is an ability to tell Jam, when you've purchased time on this machine, how to recognize the work that you want done with your computational resource that you've purchased. So in Amazon, AWS, whatever, you'll just have a login, right? You just have like a username and password. You log in, you do it all yourself, right? You don't need to like kind of tell Amazon to work, how to work out whether a login is correct or not, or whether a deployment of server or an HTTP request is good or not. You just log in and you set everything up. Well, it can't really do that on a public machine like Jam. You kind of actually have to let it understand how it can recognize good work from bad work. All we do with authorize is we just give it a function. We give it code. It runs the code, it puts the work into the code, and the code either spits out, yes, it's fine, go for it, you can use this on my computational resource that I've paid for, or no, it's not fine, throw it away. I want something else to use, my core. So that's the first stage. Once Jam has ascertained that the work is worth doing, we move into the refine stage. Both authorize and refine happen in core, which means they have lots and lots of computational power, but they are, broadly speaking, stateless. Refine can do a bunch of stuff. I'm going to go into what it does in a second, but it's like the muscly bit, right? It has processing power. It has data bandwidth. The one thing it doesn't have is coherence, because we're inside of the 6 seconds bit. We're not at the end of the 6 seconds where we're synchronizing. Accumulate is the other bit. It's this bit in between the 6 second chunks where we are now coherent. Everything that has happened in refine is now being fed into accumulate for it to gain coherence again. And necessarily accumulate therefore has to be synchronous to some degree. Otherwise we'd lose coherence just as we gained it, we would never have coherence. Finally, we have the transfers, and these are basically, this is message processing between the different elements, the different state elements inside of accumulate. I will go into that in a second. To understand how what can be deployed onto Jam, I'm going to describe Jam services. Jam services are one of 2 pieces of code that get deployed onto Jam. The first one I've already mentioned is this authorization logic, the code that recognizes good work from bad work. The second piece of code that gets deployed onto Jam is a service. A service is like a smart contract. You can think of it as quite a lot like a smart contract. It's a decentralized unit of software. Unlike a smart contract, it has 3 entry points: refine, accumulate, and on transfer. So it has the message processing one, that's last, and then it has the really hardcore performance, lots of bandwidth, but stateless one, that's refine, and then it has the synchronous, coherent one, that's accumulate. Because it has these 3 entry points, not just one, it's a bit different to a smart contract. Now I call it staged because there are different stages of computation. In each stage you can do different things. It's pipelined because 2 different stages are actually happening at the same time, just of different work packages, right? And it's distributed because it might be that even for the same service, there are multiple work packages being executed, multiple transactions for that service being processed in parallel, distributed across the network, whose outputs are only going to be resolved when they come together into accumulate at the end of this 6 second period. This is very different to smart contracts. Smart contracts are, broadly speaking, all synchronous. Yeah? And there is something that you can do when it's all synchronous. You can call into other smart contracts synchronously as well and get a result back from them. You can't do that with Jam services. Jam services compose asynchronously in general, but there are some tricks that you can do to make them compose synchronously, which I can answer if there is time at the end. And finally, as I mentioned before, Jam services, you don't pay for like gas and gas pricing. You pay for like a whole computational core. Now you can actually trade this around using agile core time, split it up, but in essence you're paying for bulk, you're paying for block computation, right? You're not paying for small little bits of a block, you're paying for a whole block. And Jam work packages actually have quite a lot more power. You can do a lot more stuff in them than you can in a regular blockchain's block. All right, Jam is permissionless, right? There is nothing stopping anyone on an instance of Jam from deploying a service to Jam. Of course, there is some, there has to be some means of managing the spam, and therefore there's going to be some economic cost associated with it. But in principle, everyone has the same access for deploying services, software onto Jam. And services are, broadly speaking, also not limited in how much code they can have, how much storage, how much stuff they can put in storage, how much data they can look up. These are only managed by deposit requirements, not by artificial limits. Services are powerful things. They're not like your average smart contract where we're just dealing with like an ERC20 or an NFT or a decentralized exchange. An example service would be the whole of Polkadot 1. This, I anticipate, will be implemented as a service on Jam. Yeah? This is a big thing. Something that can validate, 50, 100 parachains. That whole thing would be just one service. Services can be very, very powerful things. Jam doesn't care about this stuff. This is opinionated. Jam has minimum opinionation outside of its basic virtual hardware. It doesn't care about staking, doesn't care about economics, it doesn't care about governance. If these things are important, they would be implemented on top of a service, or on top of a parachain, on top of a service, right? But not on inside of the Jam protocol. The Jam protocol is meant to be minimal. Now, one of the things that Jam utilizes is the PVM. This is a very significant innovation in blockchain. But we are really standing on the shoulders of giants with it. So PVM is it's an instruction set architecture. It's basically a machine, a model of a machine that is based on RISC-V. You may be familiar with the RISC-V ISA. It's an open source ISA developed in an academic environment. It's actually seen quite a lot of hardware that has been manufactured to actually run RISC-V programs. And it's very simple. Yeah, and it's kind of extensible as well. It's quite good like that. There are lots of extensions to RISC-V, but it's basically just a RISC ISA, right? A simple machine specification. RISC-V code, it turns out, can easily be recompiled into PVM. So we actually have a PVM build system that uses existing compilers, LLVM, and everything that LLVM can compile to, can target or can take language, and every language that can use LLVM can target RISC-V and therefore can target PVM. So Rust, C, C++, there are probably others, but there are some of them. Anything that doesn't have a runtime, basically, anything that can compile to bare metal can compile to PVM. PVM has 64-bit registers. Okay, unlike EVM, which has 256-bit registers. PVM, unlike EVM, which has 256-bit stack, right? Now, it turns out having 256-bit stack doesn't make it go very fast when you're trying to make it run on regular hardware. Having 64-bit registers, and in particular, the version of the RISC-V that we have actually only has 13 usable registers, similar to the amount of usable registers on x64. It has a sensible address space, something you're familiar with, 32-bit, pageable in 4K pages address space. very similar to modern hardware. It uses the Harvard architecture, so it's got separate kind of memory for its code, and that code can't be changed. This basically gives it some degree of security over how bad bugs can get. Crucially, it can be very, very quickly, with order n, recompiled into x64 and ARM. Yeah, this means for modern silicon, we can recompile PVM into native machine code for that silicon. And we can also do dynamic metering on our implementation, and therefore other implementations should be able to reproduce it with not so much overhead, maybe about 10% speed overhead. Because the stack itself is stored inside of main memory, it's very easy to do things like continuations. It's very easy to basically just pack up the machine state, stick it in storage, and then break it out at a later stage and continue running the software. In the same way that a hypervisor would spin up a VM and then basically schedule it on and off local CPU, or be able to save it to hard disk and restore it later. And we get, on current implementation, about 45% of the speed that it would run at if it were natively compiled to that architecture. Yeah? Software running on chain that runs almost about half as fast as running it natively. If you compare that to current blockchain, you'll find it's orders of magnitude better. So if we look at the jam anatomy, and this is a bit of a lot going on in this picture, but basically you have this big refine part, this core, right, and this smaller accumulate part, the bit that happens on chain, the synchronous part. And this big part can take lots and lots of memory from the lots and lots of data from the outside world, put lots and lots of data back into it, and the core itself, the processing element, runs at about somewhere between 25 and 50% of native x64. It can also look up lots of data that if it's stored on chain, and it feeds about 8 kilobytes a second into the accumulate logic, whose job is to basically synchronize everything up, make sure everything is coherent. And for that, it gets this basically access to this on-chain database that can give it about 1 million accesses per second, right? 1 million database operations per second. And a bunch of computation as well. So yeah, Refine can accept about 12 megabytes of data, and Refine happens every 6 seconds, giving you the 2 megs a second. It can also yield, it also can output the same amount of data into distributed storage. It yields up to 48 kilobytes of data, which is fed into Accumulate. And it executes for about 5 seconds of PVM gas every 6. So every 6 seconds, we're getting between 2 and 2.5 seconds of real, honest x64 native speed computation. It can make pre-image lookups, but crucially, it can invoke other PVMs. It can create a new virtual machine, indeed as many new virtual machines as it wants, and run them. It can, if it knows what data to put in the virtual machine's memory, it can restore a previous existence of a virtual machine and carry on running it. This allows it to do something that has not been possible before in blockchain. It can do actual Turing-complete tasks. It can, if you want to put an infinite loop in there, you can, because in this inner PVM, because your inner PVM can be packed up and restored at a later date. Yeah, the block boundary is no longer an issue. We no longer have, in principle, a block gas limit. We can work around it. And this is a big deal. So Accumulate gets 10 milliseconds of PVM gas and gets all the multiple outputs from Refine in order to combine them into coherent state, into this synchronous database. It can also create other services, upgrade its code, do a bunch of other things. 5 minutes. So Jam has a authorization model that I've already sort of talked about a little bit. It's essentially, it revolves around having what we call an authorizer pool. Now, the authorizer pool is associated with every core, every computational element of JAM. When you buy JAM time on the JAM machine, you're buying the ability to place an authorizer into a particular core's authorizer pool at a particular time. The fact that there is an authorizer in a core's authorizer pool allows a class of work packages that you can decide to be accepted as being valid for computation by JAM. A work package, therefore, is only schedulable if, firstly, the authorizer that it claims to have actually, when fed the work package, says, yes, this is fine, and also if there is in that core's pool that the work package is meant to be executing on, an instance of a commitment to that authorizer. You need both of these things. And if they're true, JAM will do the work. It will process the work package. And basically what you do is you buy the ability to put the authorizer into that pool. That's where the JAM economy comes from. The output data from the authorizer code, we can output some data, give some arbitrary data out, that gets fed into Refine. If there's anything to be done, for example, you might want to punish the validator for using your authorization system to make a bad block or to do something useless. You may punish them for that, and you would need to know who it was to do so. Well, you can do that by passing data out of the authorizer into Refine. All right, very quickly, I want to talk about JAM's signature service. I've talked about JAM a lot. I haven't talked about what JAM enables so much. It's CorePlay. Now, CorePlay is really an answer. The reason that we find ourselves looking for something like CorePlay is we have to understand why are people using L2s? Why are we deploying more blockchains? We're not deploying them particularly for specialization or sovereignty. This can be they can deliver this over certain smart contract environments. But in principle, a well-designed, flexible, powerful smart contract environment need not be worse at specialization or sovereignty than a custom blockchain. The primary reason blockchains are being developed and deployed is for scaling out. They want additional volume, additional transaction throughput. Big problem with scaling out into blockchains this way is, as I've mentioned, persistent state partition or fragmentation of your ecosystem. Why is fragmentation a problem? Well, big reason, it limits network effects. It's like the further things are from each other, the harder the harder it is to gather these network effects. But more specifically, it limits use cases, it limits atomicity, the ability to atomically compose across your ecosystem. It makes developing solutions harder. And as a team, it forces you to limit yourself or commit yourself to one corner, to one sort of sub-ecosystem, and not enjoy the benefits of living in another sub-ecosystem. So what's CorePlay? Well, CorePlay is it can be likened to a few things, but in essence, it is a smart contract framework, but actually more powerful than smart contracts. These are actors. In principle, they don't have to obey a block or a transaction gas limit. They can have an infinite loop if they want. You would write them like you would write regular message processing systems. They can have regular memory that is paged in and out. And crucially, these things are elastically scalable over JAM's cores. The whole of CorePlay can grow as needed. As there are more actors doing more things, having more interactions, you use more cores. And this concept of elastic scalability is not something that has been seen before in the blockchain world. It's actually something Polkadot is pushing, though, over this year. In principle, core play can deliver global atomicity without any fragmentation. How does it do this? Essentially, it allows actors to pay to be combined synchronously, to pay to be co-scheduled. And we can do this very agilely because we're not trying to co-schedule blockchains, we're only co-scheduling smaller state machines, actors. So part of how we do it is we store all of the actors in the same data lake, yeah? And we have this coherence that Jam provides, so we can draw whatever data we need when we need it, regardless of where we are in Jam. That's a really big thing. And this is how it's different to blockchain, to this general L2 approach, where the different L2s each maintain their own data. Second, we pipeline a lot, and this is essentially this pipelining of and distribution that we do when we have many different refines being executing at the same time as accumulate in principle executing. And then thirdly, we have the PVM, allowing us to do things like computations and allowing us to really increase the amount of work that we can do in Refine. We also use much smaller state machines. Instead of using giant state machines like blockchains with gigabytes of state, we have small state machines, actors, yeah? And we can pick and choose which actors we bring together when we want to bring them together. We have regular repartitioning, every 6 seconds potentially, where we can repartition and combine actors into the same sort of groups for synchronous composition, for atomicity, as we believe they are economically sensible to combine. Actors that don't interact, there is no need for them to be in the same group. But the problem is that if they happen to be on the same L2 blockchain, then we have no choice but to co-schedule them. Yeah? With Jam, with Core Play, we can avoid that. So this is significant improvement over certain other approaches to roughly this problem. One of them being sort of multiple instances of a smart contract across on the different L2s, each with their own, maybe with some agent system out off-chain that rebalances them or synchronizes them in some way. This is not a particularly useful, sensible approach. Co-sequencing is something that's catching on in the Ethereum world, which basically is more or less a similar approach to as core play, but where your state machines that you're trying to co-schedule are not sensible sized, but they're massive sized things. And as soon as you try to co-schedule something of the size of Jam, 341 full-on blockchains, you would need a supercomputer and therefore total centralization in order to be able to co-schedule them sensibly. You would also massively suffer from suboptimal combination of actors or smart contracts living in the same L2. Yeah? You would pay a lot for this. Essentially, what you pay is oracleization. You'll be paying to oracleize the different states across into other chains, which would massively limit your throughput. It also presents a huge issue with regards to the causal entanglement. Essentially, this is an n-squared problem. Every system that you are trying to causally entangle or co-schedule would have to check all of the other systems have actually enacted or are certain to enact the causally entangled changes before that system became certain to enact those changes. Yeah? Essentially, there's kind of the problem of not wanting to be the first one over the line. You have to kind of wait until everyone's about to step over the line and actually enact the causally entangled changes before you do yourself. Otherwise, you might be stuck in a position where you've enacted the changes believing that everyone else is on the same page, and then actually they go off and do something else, and now you've sent funds away, but actually you're not going to get anything back. This essentially leads to huge amounts of centralization, and it becomes very difficult to actually do this computation on-chain. There's also intent solvers, but these solve a different problem. They kind of have some. They can be very useful for a certain class of problems, particularly when interoperability is an issue. but they, the main issue is that they don't actually allow the composition of on-chain entities, right? They don't allow this fundamental sort of self-sovereign, autonomous atomicity that we get when we do use the jam approach. Good. Oh, final thing. So why not ZK? What's up with ZK? Why don't we use ZK? I mean, I already covered this a little bit, but basically ZK is super, super expensive to use for scaling. If we want to use it for things like anonymity, privacy, all the rest of it, ZK can be an extremely useful primitive. But if we want to use it for scaling, like the actual ability to compress correctness or computation onto and reevaluate its correctness objectively and fast, it's very expensive in comparison to crypto-economic schemes like ELVs. It's about 2 million times more costly at our last estimate, which has probably gone down a little bit now because they are making substantial improvements to ZK technologies, but still we're talking orders of magnitude more expensive than doing it in a crypto-economic manner. Good, that's the talk. Thank you for your attention. Cheers. Some questions?
Thank you very much. Yeah, we will go straight away, straight next to the Q&A session. So, one question per person, and make the question technical, please. All right.
Hello, sir.
Hi.
It's a pleasure to talk with you, sir. I'm currently pursuing PBNX. So my question is, like Ethereum and Polkadot, they are both rely on traditional cryptographic security, right? So could the JAM integrate the post-quantum cryptographic algorithms to the future-proof blockchains for the security?
Mm-hmm. Yeah, it's an interesting, I mean, this was quite a hot topic at the end of last year with Google's recent advances in quantum compute. I mean, I think it's sensible to prefix this answer with, we're still some way away from a workable quantum computing system by, you know, as far as I know from what I've seen. But yes, in principle, JAM is quite a good candidate for quantum resistance. One of the things that makes it a better candidate than other systems is the fact that it's transactionless. It doesn't deal directly with user transactions or signatures, like kind of end user signature schemes. It uses its primary, it's got 4 main pieces of cryptography that it makes use of. One of them is hashing. This isn't particularly important to quantum, it's already kind of quantum resistant. And then 3 signature schemes. One of them, ED25519, is probably more or less drop-in replaceable for a regular public-private key quantum resistance scheme. And there are already such schemes standardized. The other 2 are a little bit harder. So Safrole relies on a Bandersnatch ring signature scheme. This doesn't have a quantum equivalent. And then we also have BLS. BLS is what we use in order to generate beefy proofs to make it easier to prove finality on systems like Ethereum. This also would be a bit of a tricky one. Most likely, Ethereum itself would need to introduce maybe some ZK primitive, ZK pairing functions in order, or precompiles, in order to provide a better facility for proving finality of the JAM network. And realistically, we'd need an alternative mechanism, block production mechanism to Safrole that wasn't reliant on ZK, sort of this ZK ring proof that we have with Bandersnatch. The Web3 Foundation research team, I actually already tasked them. I tasked them at the end of last year to go away and come back in a few months with a paper describing how we will manage, or a perspective for approach for replacing Safrole and managing the possibility of light client proofs onto Ethereum. But the main Safrole, it's nice. It's good to have, and it does, as I mentioned in the talk, protect us against the possibility of DOSing of validators. But in principle, it's obviously better for Jam to relent on that particular point, but be quantum resistant, than risk total breaking of it being through quantum, but still maybe have some anonymity for validators. That doesn't really make sense. So we would probably replace Safrole with a maybe something like Babe, which you already use for Polkadot, but with quantum resistant cryptography, but basic cryptography, not the anything ZK. And relent if it was like, wow, it's happening and we need a solution next month, then what we would do is basically switch ED 2551i out to a quantum resistant standardized scheme. Not try to do any light client proofs onto Ethereum quite yet, leave that for Hyperbridge, and replace Safrole with a lesser block production system like Babe. But as I said, I think we've probably still got several years before we're going to have to approach this problem.
All right, thank you so much.
Thank you. Okay, next question. Maybe somewhere in the back there.
Hey, so nice to see you. I work on the infra side of things with a few blockchain companies, so primarily setting up validators, setting up app and RPCs. In terms of, with respect to Jam, like what kind of projects or what kind of proof of concepts could I be making on the infra DevOps side of things?
So, I mean, Jam itself will need a lot of validators, 1,023 at its current model, which is about twice as many as Polkadot hosts at the moment, runs from at the moment. So there is that side of things. But very likely, one of the first truly Jam native services, beyond the Polkadot 1 compatibility service, will be this core play service. This will need a secondary network. It will need essentially this distributed co-scheduling network. And this distributed co-scheduling network, they will essentially be kind of collators, what we currently call collators for parachains. So they will be work package producers in their own right, but they won't run the Jam network. They will produce work for the Jam network to do based upon what actors exist and what transactions there are that are trying to interact with those actors. And this will be an opportunity for running infrastructure, I expect. And then, of course, there's lots of other stuff like, explorers and websites and real-time analytics and so forth. But I think if we're looking at specifically decentralized stuff, then the core play network would be an interesting thing to look at.
Thank you.
Thank you. We have time for only one more question. So who has a very good question? Okay.
Hi, I'm Shreyas. So we are building India's first immersive music streaming platform. So I have a question around adoption. So Ethereum has been a key player in metaverse, but what do you think at a large scale are major blockers to adoption of digital immersive entertainment as far as, let's say, music or gaming is concerned?
Could you repeat that but a bit slower?
The adoption basically, what are the major blockers at a large scale to adopt decentralized metaverse adoption for digital immersive entertainment?
So digital gaming? Yeah. So I mean, Polkadot's doing quite a lot of work in the digital gaming space, but what Jam, I think, what Jam can enable is a degree of throughput beyond what Polkadot can provide. And potentially enough compute power to start doing I mean, maybe not any real-time game mechanics on chain, but potentially some complex turn-based game mechanics on chain. So where we can actually reevaluate all the various logic that the game is using on chain with the player inputs, and I think this can provide some very interesting potential sort of games that otherwise wouldn't be possible. Like for example, if you want games that have some sort of economic consequence, like maybe I used to play Magic the Gathering, this kind of collectible card game, and one of the things that you used to do, at least in the old days, was you have this ante, right? So you would each basically have a card, and these cards could be pretty expensive, and you would each have a card that was sort of that you would lose to the other player if you lost the game, and this is like an economically strong outcome of the game. Now, if the game is being played on a private server that is potentially sort of hackable or influenceable or whatever, biasable, then you probably wouldn't want to play with a particularly strong economic outcome, because you would be concerned that the other player might cheat or that you weren't going to get a fair game. But if everything is being reevaluated on chain, if your randomness comes from the chain, then in principle you should be able to play even quite well, depending on how sophisticated the chain is, how much processing power it has, and so forth. You should be able to play quite sophisticated games and still not be susceptible to bias, or have a strong, credible guarantee there's no bias. And Polkadot can already do a lot of this because it's got the parachains model. But as I say, in principle, Jam can provide substantially greater levels of computation. Could perhaps push that forward.
We don't have time, unfortunately, anymore. Or do you want to take one last question?
Yeah, sure.
Okay. One real last question now. Okay, there's. Okay, they are very eager, but he was holding his hand already for longer, so he will get this question.
Good evening, Dr. Wood.
Hi.
My questions are that how will this be implemented? Would we require hard fork? What is the ETA to implement this? And how do you plan to get 1,023 validators from the current 400-ish validators?
So my expectation is that Polkadot will, when we have a Polkadot compatible service, authored, audited, and the tooling that's necessary to go with it, so Cumulus basically, Upgrade, and Polkadot SDK, a version of that which works alongside it, then we will stop the Polkadot relay chain, by which time all of the non-parachain hosting logic should have been moved off into system parachains. This is already something that's happening over 2025. And instead of being, that state would be migrated into some kind of Genesis service state for the Polkadot relay, parachain validating service that would sit in Jam. That would then be sort of migrated into this service. And then basically parachains would, presumably they've already been authoring blocks in the meantime. They would then essentially finalize their blocks by sending these into that relay chain service, which would then actually run through all of the computation that the blocks had done. It would take a little while to synchronize, but it should get there quite fast. I mean, presumably at that point, we still only have maybe 50, 60, 70 parachains. And we have 341 cores. So we can basically synchronize about 4 times the speed of parachain block production. So if it takes an hour, then we're probably going to be done in about 5 hours. And we will, parachains will basically at that point be tracking their current block into Jam and getting it processed by Jam and then making its way into the parachain service. So essentially, yes, it's not really a hard fork, but we would put a transaction onto the Polkadot relay chain, which basically caused it to stop. So we would intentionally brick the relay chain. And we would obviously only do that when we are very, very confident indeed that we would the parachains could continue being finalized on the Jam chain. The how do we get 1,000 transactors? 1,000 validators to do Jam? Well, basically, probably what we will do is just increase the Polkadot validator count to 1,000 first, and just move them over. That would seem to be the easiest way of doing things. Probably the only way of doing things. Polkadot will likely use the staking chain that exists on Polkadot at the moment, the parachain, the staking parachain. Oh, no, actually it doesn't exist yet, but it will exist this year. Would basically be used by Jam to work out who its validators are. And therefore, it would be rather complicated if it didn't already have 1,023 validator slots. So we'll very likely just increase Polkadot's validators to 1,023 first. Cheers.
Thank you very much for the questions, everyone. And before I announce the next steps for you after the jump tour, please give Gavin a big round of applause.
Thank you.
Alright, so now that you heard about what Web3
How are you feeling?
before is really
I can sign some things.
and what makes Polkadot
Do you want to just sign it with your name? Or do you want to...
No, I never sign with only my name,
Yeah,
because
that's what
otherwise
I
they'll find their way onto auction sites. I always make it out to someone.
Okay, we're going to go to that little room we had originally set up, and then I've told them that I'm allowed to bring the amount of people that's on this, there's 14 people, and we'll just do that, and then we'll go after that. Yeah? Cool. Sound good? All right.
Then we also
So sorry about the mix-up.
all available resources with you in the Polkadot ecosystem into the portal on Notion. And there you basically see how can I get funding for this, how can I get a grant. So please check it out. And then also
Bump up the
special
volume.
announcement.
Just check those
things. Blockchain Academy. They will be hosting a Jam course at the end of this year, and all of you apply.
Stuck in there. Okay, cool.
Guys, thanks so much.
It's will be the slides after the session. And with this, I'm